Well, there is.
Okay.
Let me draw this.
You will look at the face or something.
You're getting there. You got me. Yes. So, this Ike.
Yeah.
But now if you draw, draw it here. Then you're applying a voltage, no?
Yeah.
You're applying current, sorry, and you look at the voltage, right? Then you'll have V and I. This will have to be this long, I don't think. This is your V. I. This will be the voltage across the resistor.
If it's a pure resistor.
If it's a pure resistor, yeah. Assuming it's a pure resistor, yeah, right? Now, what happens? If you look at the voltage of the inductor, will it follow the same thing?
I think it's V is equal to L di by dt. So there will be 90-degree lag for the current.
Correct. Now, excuse my drawing, but I will try to draw this as nice as possible. Probably not 90 degrees, but
yeah.
But yeah, anyway, the point is that this is then I.
Yeah.
Okay. And this is your voltage. So there's a phase difference now. Can we use that? Can we use this phase difference somehow to? So okay. So let's.
So again, it will tell us whether it's it's more resistive or more inductive. That we will come to know.
If it's more inductive or more resistive, yes. But even with the impedance, pure impedance,
correct,
we can
correct
do that, right? But if you want to know if it's the permeability or the conductivity, then it's a little bit harder to do, right? That doesn't give you that information.
Correct.
So, this is the impedance, okay? Now, so ZL in that case is square root of R
square plus omega L square.
Okay. Sorry. J is 1. So this becomes omega L squared, right?
Yeah.
Or omega squared L squared. Okay?
Yeah.
Now if you draw the impedance diagram here, here you have your imaginary component, which is your omega L, and then R.
Yeah.
Serial component. Then, if you observe,
right? What is this line?
This is your.
Isn't? No. Oh, that's omega.
Yes.
Yeah.
This is R.
Yeah.
Yeah. So then this is. There is a change in angle.
Okay.
Between your L and R coordinates. Okay. So based on this, so this then phi or theta or phi, doesn't matter, right? Is omega L over RL. Now, this phase, what if I tell you, you can use this phase to determine the difference between
between permeability and whether they have different permeability or different conductivity.
Yes. How can that be? If you connect an oscilloscope, what would you see?
Some Lysagius figure. Or you can measure the phase.
So, let's say, for example, you have some specimen, okay, and then you have your primary. Let's say you have. I mean, to explain this, maybe it's easy to have two separate coils. Let's say you have your primary coil, P, okay. You have your secondary coil, S, okay. Then let's say you are now connecting this to an oscilloscope, okay, just to observe the waveforms.
So this
To a resistor.
primary is excited. Some sinusoidal source is connected to primary.
Yes. So here primary is connected to a sinusoidal. Secondary is measuring. I mean, secondary will also measure the primary field because let's say it's underneath. Then it will also measure it. But
as there is opposition from the, eddy current, it will see less and less field.
So there will be some resultant. Okay. Now, if you draw what we drew before, right, this way, VL equals I XL, and this is RL because IRL. And if I connect this to a resistor and then to an oscilloscope, this oscilloscope will see this one, right?
So this the VI is the voltage induced in the secondary coil, is it?
This one?
Huh?
This one.
Oh, that is VL.
VL.
Okay. VL is
yes. So we are talking about the secondary coil now.
Yes.
Secondary coil is connected to the oscilloscope.
So it's a voltage induced in the secondary coil.
Yes.
And R is the resistance of that coil.
It's correct.
And it has got some inductance also.
Yes. So
what is this R in the other side?
This one?
Huh?
So you're measuring
across a
resistor, right? Then if you draw the two voltages, what would it look like?
Two voltages means excitation voltage and the induced voltage, is it?
No. VL and VR.
Oh, VL and VR. VL and VR? Oh, the VR is the voltage that you're observing.
Yes.
VR will be lagging?
VR will be lagging.
Compared to VL.
So it will be like this, no? And then this will be like something like this.
Yeah.
So this phase change, right, is actually related to the conductivity of the permeability. So basically, now if you draw, again we are drawing this is VL, right?
Yeah.
And this is R. Now let's say we are looking at different materials, different conductivity materials, okay, of varying conductivity. Now, if we plot, okay, we are using VL and R, and we have this impedance plane. If we plot the impedance curves for these materials, right? Let's say you're starting with a low conductivity value and you're increasing the conductivity, right? So conductivity is increasing.
Okay.
What you will see is my drawings are not very good, but you will see this kind of curve. Now, obviously, these have their own phase change.
So this line that you've drawn,
this is for sigma, right?
Okay.
And this is for the lowest sigma value. This is for the highest sigma value.
So, but this line is Z or R?
Oh, you mean this line?
Huh?
Oh, this line is so. Sorry. My mistake. Right. So this is omega L, this is Z.
Okay. Yes.
Okay.
Got it. Yeah.
So then what? So again, we are assuming we are keeping mu constant here. Okay. Then what we observe is we'll get something like this. Different phase changes.
So as conductivity increases, it's becoming more resistive.
Yes.
Is it? Yes. Okay.
That's true, right? We talked about that before. Right? Conductivity increases, resistivity increases. So this
and the inductance reduces also.
Inductance also reduces. Correct, right? Okay. But
because that flux that you're drawn from top to bottom was reducing.
Yes.
So the flux linkage per unit current is reduced.
Yes.
So L will reduce.
Okay. Now, what do you think will happen if we draw the same thing? Okay, we have omega L here and R here. Instead of now we keep mu constant.
Okay.
And we
permeability is,
let's say we increase the permeability. What do you think to look like then? What are your thoughts? Here, when you increase the conductivity, right, as we, but with the permeability, we talked about something else.
So initially permeability is low or high?
Initially, it's low. Initially, it's low.
And for a fixed conductivity.
Yes.
I think you have to draw one line first. Then I can say which direction.
Okay. Let's say the line is like this.
Okay.
That's what the line looks like.
Now you have increased the permeability.
Yes.
From here.
Yes.
That means it will become more inductive.
Yes.
Correct. So it will go to the other side.
Yes. Yes. Exactly. Right. So as we increase permeability, so it's the opposite. So here you have the highest permeability, right? And here you have the lowest permeability.
Okay.
Low permeability and highest permeability. Is that correct? Now, what if we draw both together, omega L and R? We know when you talk about this, we have a curve like this, our conductivity curve, correct?
Yeah.
But
so it will touch somewhere. I mean the
yeah, this one. Yes. So what's interesting is that this curve is like this. It should be more closer to here. Can't draw a straight line. Let's say this is like this.
Yeah.
This will actually cross at 90 degrees. So this becomes your sigma. This becomes your mu. So now, based on this impedance diagram and the phase change, you should be able to separate the variables. Because if you are testing a material, applying the same thing, if your curve follows this, then you know it's changing because of the conductivity. But I forgot to mention one thing here, the liftoff. Right?
What is liftoff?
Liftoff is, now we saw there was a specimen and we saw there was a coil. This is basically the distance between the coil and the specimen.
Okay.
Coil.
So if that vary, then also the opposition will change.
Yes, but the interesting thing
you will think it is output due to
yes, but it's not
material change.
Yes. But the interesting thing is this liftoff, or let's say a dimensional change, is actually here, or liftoff. Also fits this curve here. So if you can fix this, and let's say if you know the permeability, right? Or rather, if you fix the permeability, then you should get a graph like this. Then you know for sure it's changing because of this. Similarly, if it's the other way around, if you fix this, but then this could be because due to this or this. So it's not possible to change the to separate mu and liftoff or the dimensional change, but it is possible to change the permeability and the.
So the gap between the coil and the test object is maintained.
Yes, ideally you want
that is,
and that is possible, right? So if you and there can be many ways of doing it, right? You could have a spring or something like this, so you make sure that it's.
There can be mechanical arrangement to take care of this.
Yes. So that's one way. So now, not only do we know the impedance.
So this is for material. I mean, you have different material, but you suspect that there is a change in conductivity. I mean, let's say 3 blocks of material, each one has got different conductivity.
Yes. You suspect.
But permeability is expected to be same for all.
Permeability,
or it may not be.
Ideally, it will be. Ideally, it will be the same. To make sure, because what you can do is you can also measure the 3 materials, and you can observe the impedance, right? And or what you can do is for known permeabilities, right? You could offset that by because what you see is let's say from oscilloscope, that phase change, right? So you can, if it's shifted, you can bring it back.
So if the impedance is decreasing, what you're saying is it shows an indication of increased conductivity.
If the impedance is decreasing, yes.
If it's the other way, it's an indication of higher permeability.
Yes. Generally. And they are generally, if you draw a graph, they are about 90 degrees. I mean, these are perfect samples, homogeneous, liftoff is same. This is all constant. Then you get something like this. I mean, this is another way. I mean, it obviously gives us more information than before. So, Bobby, you saw some kind of nice straight lines before, 90 degrees.
Yes.
In reality, it looks a little bit like this. Okay, so here,
what is the axis here?
Oh, this is still the image. The
real and image.
Real image.
Okay.
Now, and let's say you have different materials from let's say B to I.
Okay.
Yeah. A, B, B, C, D, F, G, H, I. Now.
So for B, it is already the resistance is negative, is it?
So we'll talk about that. Okay. So B, it's what you call a low conductive material, right? And then you're basically increasing the conductivity. So I is the highest conductive material. Okay. But generally what we do is, we talked about liftoff, right? The space between the coil and the specimen. And so here you can see something called liftoff traces. So what we normally do, right, when we test materials like this is you actually take the coil away from the specimen initially. Okay, so you have your specimen.
The coil alone will be there, no object nearby.
Yes. Specimen, and then you have, let's say, the coil, let's say, far away. And you measure that impedance.
So it's the impedance of the coil.
Impedance of the coil, right?
No influence due to the object.
Yes. Now, you bring the coil close to the specimen and you measure, let's say, the first material, which is B.
Okay.
Now, this liftoff trace is that change from that initial impedance
To this point.
to this point.
Okay.
Now, as we go along and you increase the... So, basically what you're doing is
So the object is the same. You are changing the liftoff. Is it?
No.
Okay.
No.
Okay.
So here what we're doing by air,
Oh.
we are basically nulling the instrument,
Yeah.
right? So we are basically saying, okay, when it's away from the specimen, this is what the impedance is. Then from the same position, but from the same position, you bring it towards the specimen.
That means liftoff is changed, or
So when you're measuring the value, then
it's at a height.
it's at a height.
Object is here.
Yes.
It's not C.
Yes.
So I got the impedance value.
Yes.
I'm nulling it.
Yes.
Okay. Then
you're bringing it
Close.
top of the close or top of the specimen, where you measure it, right? And then you measure the impedance, right?
I got Bombay B.
And now then you get specimen C,
Another object.
another object.
So coil is at same place.
Yes, but you're now comparing that to that reference value,
Which reference value?
the air value,
Okay.
right? So initially you have this, and then you measure some impedance B, right? And then you have the
Other object.
other object,
I'm again making the same line, same straight line.
same straight line. But what you can see is that as the conductivity increases, this influence of liftoff
Is reducing,
is
increasing, and then reducing.
it's increasing, right? See?
So what I should look? I should look the length of that straight line.
The
Length of the straight line. It's increasing.
Yes.
Correct.
So the higher the conductivity.
I was thinking about the real part alone.
Okay.
Okay.
Yeah. So generally the liftoff traces will increase with high conductivity. The higher the conductivity, the higher the liftoff is, because that change, because initially we're nulling the instrument, right? So from that null point to the actual measurement also depends on the conductivity, right?
If conductivity is more, change will be more.
Which is basically what you're seeing,
yes,
there, right?
Yes.
And that's all this is basically, right? But it doesn't really follow a straight line, right? You can say it's something like this. Again, it probably depends on the different materials you're testing. But based on this, right, you can probably characterize certain materials. If you have a curve.
So the line that we are drawing, is it? No.
This one, I believe, no. It's
because initially you had a value, so it's a change in. Is it?
It's, well, I guess you can think of it as change in Z, right?
Yeah. Because it's imaginary and real.
Yes.
You had a value. From there, it changed to some other value.
Yeah. The only reason I was not sure was because, it's not really straight, is it? It kind of curves.
Oh, there is a curve. Why there is a curve? It's a good point. Yeah.
I think maybe they are just traces, just to show that trace is basically increases.
Okay.
I don't think it's related to impedance.
Yeah. If it's a straight line, it may be.
Yeah, if it's a straight line,
it may be changing.
Then because we're changing impedance, right? Because obviously here you are measuring impedance, right? So, okay. So here we saw this before, this curve, increasing conductivity. But see what increasing thickness of the material does to the curve. So when the thickness of the material, right? So in the previous example, we assume the thickness is the same, right? Now, if the thickness of the material is less than the depth of penetration, remember we talked about the depth of penetration, right? You'll see that the curve will kind of shift away from the normal curve, right? If you change the thickness. Why is that? Why do you think that is?
So you are changing the thickness means the resistance of that material is different now.
Yes. Yes. So
Not resistivity, just resistance.
yes.
So the full amount of, I mean, it had a depth of penetration.
Yes.
With the original thickness, maybe it had a depth. Now the depth is reduced physically because you have removed the material.
Yes. Yes. So you're kind of
Yeah.
shifting away.
Yeah. But in case the depth of penetration was low, I mean, and you had a thick material and I removed something from here, there may not be any effect also.
Correct. So you'll probably see there's an increase in the resistor component when it's thinner.
Yeah.
Right?
Yeah.
Now, as you get thicker and thicker and thicker, what you see here is it kind of comes back into the curve until your depth of penetration is smaller than the actual material thickness, right? So basically so you can also measure the thickness of materials using this method.
Okay. So this previous plot, how is it useful, I was thinking?
I think if you have, let's say you test a whole range of materials, conductivity, let's say 1 to 10.
Yeah.
Okay.
Now, if you have a new material and wanted to know where it stands, that is a possibility.
Or if you have, let's say, an assembly line
Yeah.
with many different materials.
And you are expecting some value.
Yes.
Is it matching or not? That kind of
Confirm.
inspection you can do.
Yes.
Okay.
But again, non-destructive, right? You have a coil and a specimen. And, but then we are only talking about conductivity here. Yeah. But here, then we can also look at the thickness of the material, not just the conductivity, because that curve moves away from the original curve.